The other thing about that is if you catch a sick animal from one place, you keep it for a while, and then maybe it even kind of doesn't do very well because it's sick, and you said, well, that's not going to work, so you let it go. But you let it go somewhere else. Now you've taken the disease from the first place, and you've introduced it into a new place. So we're trying to get people to not do that. And for the same reason, you don't mix things from various places. If you really want to have critters, then get the critters from the same place, and then you're not doing any mixing. We have organisms in here. We'll never let them go. They're going to keep them until they die. And we don't go out, so we don't go out, collect some stuff, bring it in, let it go, get some more, bring it, we don't do that. And this is why. And if you really want to let something go and you haven't mixed it and it looks like it's healthy, put it back exactly where you found it, and then it has a chance, and it also won't spread disease. All right? So there's my little herp conservation plea. But let me dwell on wetlands. And I made good use of this series over the years. This was actually from about the year 2000 when we'd had a wetland symposium up in Chicago, and we generated some material for that, and that's where this comes from. But what I like to do here is follow the life history of one species of frog throughout the year and show you how the life history of the organism relates to the habitat that it lives in. So our critter is the wood frog, which occurs in any substantive, healthy forest in northeast Indiana. So this is a picture of a wetland, but it's a picture of a wetland in the middle of the winter. And around here, classically, the wetlands fill in the spring. So if you go to a place like this woman is holding a placard that says December 30th, there isn't any water. But there is this log with this cut in it and this tree that's tilted over, and we can use those as landmarks as we go. And so here's somewhere about now, and there's a skin of ice on this that this person has had to walk through, but you can still see the same log, the same trees, that kind of stuff. And so now you would look at it and you'd at least say, okay, there's water in there. You still might not think it's a wetland, it's just, it rained, it got water in it. But let's mix our species in there. By now, and by now I mean like today, most species of salamander are done breeding. So you're trying to stay warm. Those salamanders they've come out of the woods, they've had sex, they've laid eggs. Many of the species have already gone back into the woods. So the eggs are already in there, and I think that's pretty cool.
Question.
Yeah.
Salamanders sleep in the winter, right?
Well, they overwinter would be the conservative thing to say. Yeah, they slow down a lot. They're underground, so whether they stop completely, I wouldn't say that they do, because they can tolerate real cold temperatures. So now, starting about now, we'll start to get spring peepers and chorus frogs, and then before long after that, we get these wood frogs, et cetera, et cetera, et cetera. And they lay thousands of eggs in these things. And then by the time you get to the middle of the summer, then everybody's going to go, okay, yeah, that's a wetland. It has water in it. There's vegetation. Okay, it's a wetland. There's our log floating around. There's the cut, and there's the forked tree. The other part of it is underwater. And when all this is going on, then for some species in a very short amount of time, but in others for longer, they metamorphose through these stages. We start out classically with an herbivorous tadpole, and then they turn into eventually a little frog. But in between, the tail gets absorbed, they pop out these legs, their head switches from being herbivorous to carnivorous or insectivorous. And this little fellow, I say that with confidence, maybe her name is Francine, I don't know. But this little tadpole actually can't eat. It's in between being herbivorous and insectivorous. It's in the metamorphic Netherlands. And then in the fall, you go back and the water's gone. It's dried and drained out. And you might think that it is therefore worthless. But all of those salamanders, all of these different species of frog have come at different times, laid their eggs, had their tadpoles, and they have left the wetland and gone on their merry way before it dried out, at least usually, or even some of the time. These things, when you're an amphibian, life is precarious. But if you did not have this kind of a wetland, you would not have many, many species of Indiana's amphibian and many species of Indiana's reptile who eat Indiana's amphibians, and dragonfly larvae, and just all kinds of things. So these wetlands are really important. And otherwise, they get out in the wood frog babies are little tiny things that look like little tiny copies of the adults, and within a year or two, they grow up and they're ready to reproduce themselves. Now, the last thing I like to say about winter is that some species, a handful of species, including the wood frog, don't overwinter in the water. Now, there's a question about sleeping or overwintering in the winter. A lot of species go back to the water and they go down into the mud and they don't do anything all winter long. This species actually burrows down in the soil and freezes. And the notion that a vertebrate would freeze and live is, I think, pretty cool. And it is true that if you took a frog like this and you brought it in here for us to look at first the heart would not be beating, it wouldn't be breathing. It thaws, and then the heart starts to beat, and it starts to breathe, and it's fine. If you deep freeze it, you'll kill it. But in these situations, it's just below zero, and these guys can handle that. Yeah?
What's the lifespan typical or otherwise?
I'm going to make a number up and say 10 or 15 years, because that's a complicated, to give you a really good answer to that is complicated, because almost all of them get eaten right away. But if you keep it in captivity, or it's very lucky, it might live that long or longer. We now know that some of the species of turtle that we have around here live longer than humans do. But that's a very lucky turtle. And I'm going to digress from amphibians for a second and talk about some of the reptiles I work on, because I had come up with this series of slides that I wanted to share with you. So in case I don't bring it up again, that's a Blanding's turtle. That's a candidate for federal listing. Spotted turtle, candidate for federal listing. That's a leopard frog. We'll see this guy later. We'll see a couple of these later. But that's the eastern Massasauga. That's our one venomous snake that we have around here. And there's a diamondback water snake that looks like it could be really dangerous, but it isn't. Although if it bites you, you'd be unhappy. And here's the copperbelly that I think I could claim to be the nation's expert on this species. Here's the Massasauga again, another species that I'm an expert on. Our turtles, Blanny's turtle, spotted turtle. These species, I think, within the next few years will be federally listed as threatened. And so one thing that how many of you know Christine Barlow? Anybody? A couple people. She was one of my first grad students, and now she's, I think she heads biology across the street. But this is data from her master's thesis. And the red triangles are for spotted turtles, and the blue squares are for Blanding's turtles, and the plastron is the bottom part of the shell, and you can get a proxy for how big a turtle is by saying how long the plastron is. So this is how big the turtle is, and this is the average water depth for an entire season's worth of telemetry, where Chris went back over and over again and found the same turtle over and over again, and then we averaged the points for that turtle. So over a couple of years, all those dots you see are each unique turtles. And what we see is that for the real small turtles, they're in very shallow water. And in fact, so 2.5 centimeters is an inch. So this is 4 inches of water, 8 inches of water, a foot. And these are the average depths. Our spotted turtles are a bit bigger. These guys are only a few years old. These are adult spotted turtles. These are teenagers in the Blanding's turtles, and these are the adults. And what you should see is that there's a very nice linear relationship between how big the turtle is and how deep the water is that it lives in. And what you should also appreciate is that water is not very deep. So our biggest turtles on average were in water that was this deep. Or let's see, take that back, to your knee. So anytime you look out at a body of water, like a lake, these guys don't use that. All they're using is this shallow water like we have in these wetlands. So that's an important message. And that leads me to put the little guys in very shallow water, the teenagers in slightly deeper water, and then the adults in 1.5 foot of water. And then I can throw other species on there, copperbellies, spotted turtles, Massasaugas are on the shoreline, Kirtland snakes are on the shoreline, Butler's garter snakes are on the shoreline. So what you should see is that there isn't anybody over to the right. And so if we spread them out so you can see them, there they are. And nobody's in water that's more than 1.5 foot deep. And most of these organisms are in really shallow water. My point is that really shallow water is important. And if we add the axis of what I call flashiness, and that is how quickly the water rises and falls depending on rainfall and things like that, then it turns out that the little baby Blanding's turtles don't like flashy situations. The teenagers tolerate it a little bit more, and they like a little bit deeper water. The adult Blanding's turtles are more flexible. Spotted turtles don't like flashy water. Copperbellies are the most flexible, and so you see them in a lot of situations. But then Massasaugas are back down on shore and not in flashy situations. Same for Kirtland snakes, same for Butler snakes. So what we need to do is protect these shallow systems that you might not look into the woods and think those are very valuable, but they're really valuable. and we've lost almost all of them in the state of Indiana. So we have maybe 3% of what we used to have. So when people are talking about wetlands legislation that gets rid of wetlands, or they're developing something where they're getting rid of wetlands, remember this. The connectivity is important, and this is an illustration for you to show that. Here's a well-connected riparian corridor, and here's a disconnected one. The animals need to move around and use these sort of situations. So when you look at something like this river corridor, the fact that this riparian zone is forested is really important. And how many of you are aware of the River Ventures development downtown? Yeah, more of you. That one of the problems is it's going to degrade this kind of connectivity. That development actually has quite a few problems, but this is one of them.
Is a river without connectivity is more flashy too? The water levels?
It actually could be, but mostly indirectly because of that. But and that actually will feed on each other. A flashy system will erode and destroy habitat, and the lack of habitat will lead to flooding. So it's like a vicious sort of circle. All right, getting back on track with amphibians, a little look at disease. A real bad one is chytrid. And chytrid is the name associated with you'll also hear people call it B-sal, but it's Batrachochytrium salamandrivirans. I didn't do that right. Salamandrivorans. I should have practiced. But you can see why people call it B-sal or chytrid. But what it does is it causes lesions on the animal, and it degrades the ability of the skin to do various skin functions, and then the animal dies from secondary infections or complications. And actually, when you hear about white nose syndrome or chytrid or a lot of these things, the infection itself may not be what kills the organism. What it does is debilitate it and make it vulnerable to a whole variety of things that are out there. There isn't, in a way, that you could apply it out in nature. For some of these diseases, you could treat them if you had them in hand, but even then, a lot of times they die anyway. So what we want to do is not have them ever see the disease because it'll kill them, except there are species that are resistant because they have co-evolved with the disease in their home location. So you take something like fire-bellied newts, which are amazingly beautiful, and you keep them as pets, and then somebody mixes them with native animals and somebody gets let go, or there's somebody hands a disease around like we do amongst ourselves, and it gets out into the environment. And here's what you would call a heat map, and where it's red, the prevalence of chytrid in salamanders is really prevalent. So you see an area in the southeast and also the Pacific Northwest, and those are associated with major ports of entry of exotic amphibians and reptiles, and then the diseases get out and they get into nature. So I'm trying to connect for you the different things about what you're responsible for if you have pets, and that you should try to keep them, and you should not try to mix them with native species and all that kind of stuff. It's all connected. All right. So there's some gloom and doom for you. So a little bit. So here's how I'm going to do the rest of the evening. I've introduced amphibians to you. Now I want to introduce reptiles to you. And then we'll take a break, and then we'll do kind of a tour of salamanders, then frogs, then turtles, and lizards and snakes. And that's the rest. Oh my, oh yeah. Oh yeah. So that's what I'll do, and I'll throw in at least one break, if not two. And then right around midnight, you all get a snack, and then we keep going. So I've told you a little bit about amphibians. Now I need to get to reptiles, and there are some characteristic of reptiles that you would identify with them, but they may or may not be robust. And so bear with me while I talk about amniotes instead of reptiles. Let's see.
Could you repeat again what amniotes are?
Well, that is exactly what I'm going to talk about now. So, to cut to the chase and unbury the lead, it has to do with the amniotic egg. So we have an amniotic egg. Birds have an amniotic egg. Reptiles have an amniotic egg. Amphibians do not. So the amniotic egg is a unique derived character that defines reptiles as distinct from amphibians. Other things we might talk about are like dry skin. That's a pretty good character compared to a frog, because most frogs will lose moisture about the same rate as a sponge, a wet sponge. And that's not at all true of something like a lizard. But talking about wet or dry skin is kind of difficult to work with. But reptiles do have a more resistant skin due to the fact that they have a lot more keratin in the epidermis. And that helps them be water resistant. But the amniotic egg is a good, robust character for all these guys. And what that means is, unlike a fish or an amphibian, there's one more step in embryonic development where there's this extra fold that comes together and fuses, and it leads to the amniotic cavity. So when you talk about amniotic fluid, that's where that comes from. That cavity does not exist in amphibians and fish, and amongst other things, it provides a aqueous environment for the embryo to move around in that these other groups don't have. So that's what we call a robust character. But to relax a little bit, you're looking for dry skin, you're looking for scales, but the scales now are the hard part of the scale of most reptiles is from the epidermis, not from the dermis. And they have amniotic eggs, and they may or may not be shelled. So when I talk about something being shelled, I'm talking about something like a chicken egg. So in a chicken egg, you have a what I would call a calcareous shell, but what I mean by that is that the outer shell has calcium crystals in it. And so that's a shelled egg, but there are plenty of reptiles that don't have shells on their eggs. And the other thing I'll say when I talked about a shelled egg is that what you'll find with reptile eggs is if you touch them, they're kind of flexible. They're not stiff like a chicken egg is. So the way that it's put together is a little bit different. But if snakes lay eggs, what they're doing is before the egg comes out, a calcium is added to the outer shell, and then they lay the eggs. But if they are what's called, some version of live bearing, what they're doing is they don't have the shelled egg, and they just retain the eggs inside of them until they develop further, and then when they're giving birth, the egg opens, and out comes the new little youngster. But that whole time they were still in an egg. Unlike with us, with humans, there's the umbilical cord, that's true, but there's no, egg or kind of shell or anything like that in there, and then you have that direct connection to mom. So it's actually a very different kind of a situation. The other thing, to help you understand reptiles, and to some extent amphibians, is to get you Physiological Ecology 101. And so reptiles, like a lizard, is an ectotherm. And ectothermy means heat from the outside. Endothermy means heat from the inside. So if you are a lizard and you want to be warm, you're going to have to go somewhere where it's warm. Like you're going to have to sit in the sun. So if you take our lizard and you put it in here, it's just going to be basically the temperature of the room. You take a mouse in here, and the mouse is warmer than we are. The mouse is like 39, 40 degrees Celsius. And that's because it's generating heat. And the ecological thing about this that I think is interesting is, so a reptile has to import heat. And a mouse or a bird is exporting heat. It's trying to get rid of heat so it doesn't overheat. A reptile has to go harvest it somehow, typically by being in the sun.